So how do we differentiate this log function? Okay. If y is equal to the log of function x, and remember, I haven't written a base down there, so we're assuming I'm talking about a natural logarithm here. So if y is equal to the log of function x, the derivative becomes this. It's interesting. The log, if you like, sort of disappears. It's the derivative over the original function. So whatever you're logging, that function is on the bottom, and the derivative goes on top. So derivative over the function. But that's if it's a natural log, and the vast majority, in fact, 99.872349821% of the time, I've tested that, there'll be natural logs that they ask you. Okay? If they don't, on the remote chance that they don't, so if it's some other base, we still do it the same way, the derivative over the function, but we also divide by the natural log of whatever the base is. And so that's why we don't see the log in the first one, because we're saying the natural log of the base, well, the base here is e, so log e base e is 1. And that's why it doesn't appear there. So it's a reasonably simple thing to differentiate. So y equals the log of 3x plus 5, derivative over function. 3 over 3x plus 5. That's its derivative. Log of x cubed. There's a couple of ways you can do this. Derivative over function, so 3x squared on x cubed, and that of course tidies up to be 3 over x. Or I could have used my log laws, and before I differentiated, I could have brought the power to the front. I went, oh, that's the same as 3 times log of x. And then differentiate the log of x, and that would have been derivative over function, 1 over x, times 3, and we get the same answer. So it's just a matter of choice, I suppose, whether you use your log laws first, then differentiate, or just differentiate it. Depends on the function. Ooh, log. So the log of log x, derivative over the function. Now, what's the function in this case? Log x. So we've got to find the derivative of that to put on the top of the fraction. Well, what's the derivative of log x? Oh, that's derivative over function, which would be... So we get 1 on x, the derivative, over the function log x, and tidying that up, we get 1 on x log x. The log of x plus 3, x plus 2. Okay. Derivative over the function. Now, when I do the derivative here, I'm going to use the product rule. So write down the first, diff the second, plus write down the second, diff the first. Tidying the top up, I get 2x plus 5. Or I could use my log laws and break them up into 2 logs, and it becomes the log of x plus 3 plus the log of x plus 2. And then to differentiate that, each individually is derivative over function. So 1 on x plus 3 plus 1 over x plus 2. If I then do some algebraic fractions, I end up with the same result. I suppose it all depends on what I'm going to do with the derivative. If I want to find stationary points, so maybe we're drawing a curve or something like that, and we said, okay, well, to find stationary points, we're going to make the derivative equals 0. Now, in that case, I would like it as a whole fraction, because a fraction equals 0, it's the top of the fraction equals 0. But if all I'm doing is trying to find the value of the derivative, I want to see, is the curve increasing, is it decreasing, then 1 on x plus 3 plus 1 on x plus 2 is good enough to do that. So in that case, that's probably a quicker way of getting to my final answer. So it all depends what I'm going to use the derivative for, whether I split it up first or leave it. Similar with this one, because if I leave it like this, when I differentiate, I'm going to have to use the quotient rule. And look what happens. Derivative on the function. Well, the function x plus 5 on x plus 2, look what's on the top. Square the bottom, write down the bottom, diff the top, minus write down the top and diff the bottom. All right, let's tidy it up. I'm going to invert and multiply, because fractions on fractions is horrible. So turn the bottom upside down, x plus 2, x plus 5. The top one, the top of it tidies up to be negative 3. Now I can see the x plus 2s are going to cancel. Minus 3 on x plus 2, x plus 5. Had I decided to use my log laws first, then I would have split it up. I would have got log of x plus 5 minus log of x plus 2. Again, differentiate each of those. It's just 1 on x plus 5 minus 1 on x plus 2. Algebraic fraction. I'll leave it to you to decide which way you think would have been an easier way of doing it. They both involve some algebraic manipulation. Maybe it's just a matter of personal choice. Here's one where the base is not e. So remember I said, well, we'll just do it exactly the same way, derivative over the function, but then on the bottom of the fraction we'll also have the log, the natural log of the base. So log 10 in this case. And the 6's will cancel, and we get 1 on x log 10.